and you should blame me for it. But anything that I say right, there's really a whole team of collaborators working together on thinking about these problems, and I'll mention them at the end. But I'm going to say focus on linear time invariant systems, because I think that's a place where we can play and really think about certain concepts. So my talk today should be very concept-driven, and hopefully these concepts can be clear, and I can make some points. So motivation for these ideas is coming from a couple of places. One of them is the fact that, you know, we are just inundated with big data. It's all around us. There's lots of big data applications that we're interested in. One of these areas has to do with identifying chemical reaction networks. So this is an area that I've thought a bit about lately and done some work there. In this area, the nodes of this graph relate to chemical species. Edges in the graph that correspond to different reaction pathways. And then there are many networks that biologists think about when they think about, you know, what these organic machines are doing. And we're interested in understanding somehow those networks. But another set of applications are the fact that as engineers, we've been building the most complex engineering systems humanity has ever seen. And in doing that, new problems have emerged. And so kind of the complex systems that we're building and distributed control problems on those systems are also motivation for some of the things I'll be talking about today. Here I'm showing one application dealing with communication networks, but other examples include manufacturing, financial systems, you know, critical infrastructure. There's a number. You can be thinking of swarms of UAVs or a number of other different applications. So the outline of my talk, really what I want to talk about, comes in two parts. And I understand that if I'm not done, you'll just leave at the end anyway, so it's okay. Maybe we'll only get through the first part. But the first part of my talk is really a tutorial. And it's a tutorial to talk about the nature of structure and dynamics in systems using linear time invariant systems as our test bed, our sandbox to play in. But then the second part really is a bit shorter, and it just kind of describes some of our research results in addressing some of those issues that I identified in the first part. So first I'll talk about system representations, and I'll try to ask the question, what is system structure, and see if we can think through that carefully. We'll talk about the problem of finding structure from data, and then I will introduce a new kind of representation of linear time invariant systems that we call the Dynamical Structure Function. And because of the presence of this new representation, this new mathematical representation, that introduces new theoretical questions, and I'll try to make those questions clear. Then in the second part of my talk, I'll discuss some of our work in answering some of those questions. So we'll talk about informativity conditions for network reconstruction. We'll talk a little bit about a robust reconstruction procedure and how that works. We'll discuss, just very briefly, some of our results on minimal structural realization, which is one of the problems that I'll identify. And then we'll talk about some robustness, vulnerability, and security problems that emerge, and then new results for decentralized control if we have time to get through that. Okay, so I want to talk about a basic, simple system. Here's a system. And when I show you the system, here's what the picture means. Each round circle, each node, represents a function of time. U's are my inputs, Y's are my outputs, X are state variables internal to the system. So each one of these is a function of time. The arrows show how they're influencing each other. And you may be familiar with one representation that we may have to describe such a system would be its state space realization, which is a set of coupled differential equations. These are ordinary differential equations. The dot here means the usual time derivative. And we may describe something like this. Can I just see real quick by show of hands, are you familiar with state space? If I say this, is it like something you've seen before or you're familiar with? Could I just see by show of hands? Okay, that gives me some way to calibrate. Again, I come from a computer science department, and it's not always clear what people's background is, so I have to ask. So another representation for the same system might be a transfer function. So I want to point out a couple of things. Notice that these are now capital U's, not little u's. And these are capital Y's. And this is rather standard notation. This S is floating around in this matrix. Can I see by show of hands, has anyone seen this before? Okay, so if I say that these are the Laplace transforms, and you're familiar with what a transfer function is, okay. All right, because I'm going to be talking about these two different representations quite a bit, so I want to make sure that we're on the same page. So these are two representations of the same system. And the question that might be motivated by looking at this system is, what is system structure? When we say we have this system sitting on our table, and we say we want to know the structure of the system, what do we mean? Okay? So one thing we might mean would be the structure that I'll call the complete computational structure. And what that means, in blue here, I'm describing the meaning of that word. And the meaning is something like the physical interconnection. Okay, not quite, but that's pretty close. Okay, so when we look at these matrices in the state space realization, it's really the sparsity structure of these matrices that captures the interconnection, what we mean by the interconnection structure of this system. So for example, the blue matrix here, which I'll refer to loosely as the B matrix, somehow captures the links between U and X, between the inputs and the state variables. The red matrix captures the interconnections between state variables themselves, and the green matrix is somehow capturing links from the state variables to the output variables. And we can see that the sparsity structure, that is, the presence of zeros, where the zeros occur in these matrices, are really describing something very specific. You see, they're describing the kinds of edges that could have been in our system, but aren't. Because the way this system was built, we did not have any edges there. So somehow the sparsity structure of these matrices are telling us the physical interconnection structure of our system. So here we see a lot of zeros, and there's a lot of edges that could have been there between inputs to state variables, but are missing. And likewise, from state variables to outputs, we also see the edges that are missing. So one notion of structure that we might mean could be this complete computational structure, which is making a reference to the sparsity structure of the state space realization. That's really where it comes from. And that might be what we mean when we say, tell me about the structure of my system. But we might not mean that. We might mean something else. We might look at the transfer function, and what we might be referring to is the sparsity pattern of the transfer function when we say structure. And this also has meaning, but it's a different meaning. It means the closed loop paths from inputs to outputs. So when we look at a transfer function, we can't see inside the box. But let's suppose we could. And if we look inside our box there, and then we hit the first input with the signal, and we see how it propagates through the system, we see all three outputs are affected, then we can take note of the closed loop paths from the first input to which outputs were affected. And we see that reflected in the fact that in the first column of this transfer function matrix, there are no zeros. The first input affects all three outputs. Likewise, we could hit the second input similarly, and we know that it does not affect the first input, so we see 0 in the first spot, but the other two are non-zero. And likewise, for the third column, we see something similar. So in this sense, the sparsity structure of the transfer function is revealing missing closed loop paths in our system. We don't know what's actually going on inside our system. But when we see these zeros here in the transfer function, we know there was no path from that input to that output. And that sparsity structure is telling us a different kind of structure of our system. Okay. Well, these two notions of structure are fundamental. Engineers have been using these representations for a very long time. We talk about systems this way, and oftentimes, as we collaborate with other disciplines, they want to know the structure of their system, and they'll ask us to help them. And we need to understand, well, what do they mean? And as we look at these two notions of structure, we can understand that these are actually weaker and stronger versions of each other. Meaning, this is a weak version of that structure. And if we have that structure, we certainly can derive this one, but not the other way around. So this is weaker, and that's stronger. And then an obvious question we might ask is, well, when people do network reconstruction, when they run algorithms from data, to try to figure out the structure of some complex system, which structure are they actually looking for? What answer do those algorithms give them? Okay. So let's suppose we take the representations of our system and we line them up. From weakest, the transfer function has the weakest notion of structure, and then we line them up where this is increasing structural informativity, and somewhere up here we have a state realization that really tells us somehow the physical interconnection of our system. Now, we might consider the world of data and the world of models, and all of these would be models of our system. And data somehow, I'm going to differentiate in this lecture, I'm going to treat it differently than a model for now. And we may consider a class of problems that I hope maybe you're familiar with, and we call system identification. This is the process of going from data to get a model. We usually take input-output data, and we use different algorithmic procedures to get a model of our system. Now, there's lots of technical issues associated with system identification, okay? And these are not to be overlooked. There's a rich literature, a rich history here that's important for us to understand. However, the input-output data gives us an input-output representation, ultimately, of our system, which is the transfer function. It's a weak notion of structure of the system. Yet, somehow, maybe in the last 10 years, we've developed a number of other algorithms that are very similar to these identification algorithms that try to somehow find a stronger notion of structure, try to find structure, and have a little told us which structure we're talking about. So for example, computations like taking the correlations among outputs to see which signals affect which other signals. Okay. Or computing like the normalized mutual information between these signals. These kinds of computations ultimately are the kinds of computations that will find the input-output structure, the sparsity pattern of the transfer function. And I hope to make that clear and convincing through a simple example. So here's our system that we have. Notice the system has a special structure. It's a chain. So x1 affects x2 and x2 affects x3, but not back. Okay, so it's a chain structure. So in this system, if we ran an experiment where we kicked the first input with a step and keep the others at 0, we would get those kinds of outputs. And then if we kind of just treated these outputs as a vector of data and kind of naively computed things like correlations or normalized mutual information, we would see these kinds of numbers. And we could store those. And then we could run another experiment and kick the second input with a step and look at the outputs and then compute naively kind of the correlations and normalized mutual information. And we could do the same thing with a third and compute those numbers. And when we aggregate those numbers and put them into a matrix, these are the matrices we would see. Now you might think, okay, well there's a bunch of zeros at the top half of this, and so maybe it's these zeros right here. Maybe we found something going on with the structure of the system over there, the way it's physically interconnected. But in fact, it's not. In fact, these zeros correspond to these zeros in the transfer function. We know it's not this one because notice the bottom left is definitely not 0, but this one is. Now, just to convince you that that's in fact what these kinds of computations are looking for, let's put a loop on the structure. Now, when we add that edge, what we did is we just added an edge from x3 to x1. So the transfer function changes. Now we see that the transfer function in fact has no zeros. It's completely full. Because every input really does have a path to every output now. Because it's a ring. It's no longer a chain, it's a ring. We close the loop inside. So now we see that there's no zeros here, and if we repeat the set of experiments, so let me just point out before we go there, that in fact this ring is very structured still. I mean, there's a definite sparsity pattern here, that the physical interconnection of the ring is still a very structured system. It's not like every node's talking to every other node. It's still a very structured system, but we don't see that structure at the input-output level. We just see here, we see every input does affect every output. Okay? But if we repeat the set of experiments where we kick the first input with a step, measure the outputs, kick the second input with a step, measure the outputs, kick the third input with a step and measure the outputs. Now, when we look at correlations and mutual information, we see full matrices. So, in fact, these kinds of computations are finding the sparsity pattern of the transfer function. And this is before we put any noise, any kind of stochasticity. There's none of that going on here. It's just what are these computations actually looking for in the ideal case? And they're looking for this kind of structure, not this kind of structure. Okay, so correlation and mutual information methods are trying to find the sparsity pattern of the transfer function. They are not finding the sparsity pattern of the state realization. However, we know that that's a very weak notion of structure. We know that we would really like to have this notion of structure. That's much more informative for us. So how do we get from here to there? Well, it's a classic problem in systems theory. It's the realization problem. And we know a lot about this problem. We know, for example, that every state space realization uniquely specifies a transfer function. And this is the formula that gives it to us. If you tell me A, B, C, and D, I'll tell you G. It's right here. However, the other direction is not uniquely specified. We know that even if we restrict our attention to minimal realizations, that is to say, realizations with the fewest number of states needed to actually deliver the transfer function that we're given. Even in that situation, we know that this problem of going from the transfer function to the state realization is ill-posed. Because in fact, any realization that you have that generates the given transfer function, you can perform a state transformation and you'll get another one. And there's an infinite number of them. Because any invertible matrix T gives you a valid state transformation. And so I've got a whole mess of these state realizations that all generate the same transfer function. So and they all have different structures. They have different sparsity patterns to their A, B, C, and D matrices. So if I have a transfer function that I've identified from data, how in the world am I going to figure out which one of those were actually the physical interconnection that gave me this input-output behavior that I've measured and observed? That's the question we want to ask. And the answer is simple. You assume full state measurements. You need to assume that you measure every state variable and nothing else. Because if you make that assumption, then in fact there is a one-to-one correspondence between the state realizations and the transfer functions. So now when I use my favorite system identification technique and use input-output data to get an input-output map, I've also identified a unique state space realization associated with that particular transfer function. So if I can make this assumption, then I'm safe. And this assumption is in fact necessary. Okay. But we're working with biologists. And biologists say, yeah, but I'm measuring 99 of the 100 variables that might be there. If I just miss one, and then I do it, don't I practically get close? Whatever network, okay, so maybe it's not exactly the right network, but maybe, come on, it's close, right? It should be. Because I'm measuring so much. I don't want just one. Wouldn't that be okay? Well, even if you mistakenly assume full state measurements and you've only missed one state variable, your conclusions could be arbitrarily wrong. So here's a simple example. We have this transfer function with 3 states. The physical interconnection that we see, we only see 2 of the states, and we just want to know how are they connected? Are these edges there or not there? And this is the data that we see from an experiment that we do. So can we take this data and can we figure out which of these might be real edges in our system? Well, in fact, here are 2 different realizations of that same transfer function. They're exact. They deliver this exact transfer function. Here, in this realization, the input affects a hidden node that I'm not measuring, and then that hidden node affects each of the other measured nodes independently. This structure, clearly, these are decoupled, completely independent. They do not affect each other. But this other realization here, my input affects a hidden node, and then that node affects both of these, but these affect each other, and they're affecting the hidden node. And in fact, in this realization, you shouldn't have these two edges there. They do affect each other. Well, they're both realizations of the same transfer function. There's no information, there's no experiment I can do that's going to somehow tell me from input-output data which one of these was really there. Because whatever experiment I do on the one, the other one would have given me the same response. Now, you might think, well, maybe that's just because this is only a size 3 system. You know, like, so missing 1 is still missing a lot. You're missing a third of the states. But you can generalize this example, this structure right here, which generalizes the previous one, and you have n nodes. This will be completely decoupled. And then nearly any state transformation on that system that preserves these outputs and only really changes that last hidden state, the basis that the hidden state is working in, any transformation will pretty much scramble this and make it fully connected. And anything in between is possible. So in fact, this assumption of full state measurements is necessary. It's a pretty strong assumption, and it really needs to be there. So you have input-output methods that give us a weak characterization of system structure. Or if you want to know how things are really physically interconnected, you need to make a very strong assumption that you're really measuring everything that's there. So what we really want is something in between. We want a representation of systems that gives us more structure than these, but to recover them from data doesn't make you kind of like, you know, sell your firstborn, you know, give up children, or anything like that. You just want to make a reasonable assumption to be able to recover this. So we developed such a representation that we call it the Dynamical Structure Function. And it's represented by two matrices that are like G, they're like transfer function matrices. So they're matrices that are real rational functions in the Laplace variable. Q is a square matrix of the size P, where P is the number of measurements that you make, so it's P by P. And capital P here is the input matrix, and it's of size M by P, so it tells you it's the same size as G, essentially. Okay, so this is a new representation for systems, and it's more structurally informative. It really solves the problem that we want to. Let's look at what it really is through an example. So let's suppose I have this system sitting around. This is the complete computational structure. The bright purple nodes are the ones that I'm measuring. I'm measuring 5 of them. The dark blue ones are hidden states, and the white ones are the inputs that I can affect. Now, if this is the complete computational structure for my system, my state realization might look like this. So this is hard to see, but you can see here that where there's non-zero entries, that basically will correspond to the adjacency structure of that graph. Okay, so that's the way to read this. There's 13 states, and these are the derivatives. It's the usual state representation. Well, I want a new kind of structure that I'll call the signal structure. And what I want is I want to make no assumptions about the hidden states, and I want it to describe the hidden paths among manifest variables. Let me show you what I mean. So here are the 5 variables of that system that I'm measuring. Well, if there's a path from one to the other that only goes through hidden states, then I want to draw an arrow. So for example, from 1 to 4, there's a path that goes through 8. So I'll draw that arrow. And from 2 to 4, there's a path. It also goes through 8. So I'll draw that arrow. And so forth. And when I draw all my arrows, I have to label them not with real numbers the way this one is labeled, but I have to label them with transfer functions because there's dynamics on these edges, because there's hidden states on that pathway. So I label them with transfer functions that I'll call Q. And I'll call that my internal structure. And then likewise from the inputs to these measured outputs, I can do the same thing, and that gives me P, my control structure. Now I want you to notice that the adjacency structure of this is not somehow easily derived by just looking at the state matrices over here. It's not like I can just partition the first 5 states and then grab this adjacency structure and somehow see this picture. Right? Because this is diagonal. So the information's there, but it's not like it's just obviously looking at you. You have to do something to get this picture. And I also want to point out that this notion of structure that I'm talking about here is not the usual kind of intermediate structure that we talk about. As engineers, we normally talk about block diagrams, and we put things in boxes. And we look at structure as being the interconnection of subsystems. Okay? So if we did that with this system, those boxes right there would be how we kind of condense the graph, and mathematically it's called the condensation graph. But we draw it as a block diagram like this, but we turn that into this picture. But this picture and this picture are quite different in some fundamental ways. This notion of structure that I call subsystem structure demands that you've actually found exactly which box each hidden state belongs to and put it in that box and only that box. So for example, the state number 8, which is right here in the middle, that state is inside a box S4. But on this picture, that state 8 is in this transfer function. It's also in this transfer function. It's also in this transfer function. And you might think, well, that's not good. We want to know where state 8 goes. We would like to know that. And it's true. We would prefer to know that. But the amount of information necessary to recover that structure from data is actually harder in general than recovering the original state space equations. That's very hard to get from data, whereas this is actually quite easy. By being agnostic, by being willing to not say exactly where each hidden state has to go, we can answer the question of how measured variables are causally related to each other. And that's a valuable notion of structure. So the kind of Q and P matrices we'd be looking for here would look like this. It would say Y depends in this way on the other Y's, and this is the adjacency structure of the red arrows in that picture, plus this adjacency structure of the brown arrows times the inputs. We want something like this to describe this notion of structure. And so how do we get that? Well, we begin from a state realization. In this state realization, we measure the first some number P state variables. Those are our measured outputs, what we call Y. And then the other one that we'll measure we'll call Z. And I partition my state matrices commensurate with that notion of what I'm measuring and what I'm not. So that's what that is right up there. Now what we do is we take Laplace transforms. We've assumed zero initial conditions to get that on the left. We then solve the bottom equation for Z. Just a little bit of algebra, taking it over there. We know SI minus A22 is invertible Y. Because A22 is a bunch of real numbers. It won't have the S's, right? There's no cancellation that can happen there. So we know that that's always invertible. Now we substitute it into the first equation for Z. And now Z is eliminated from that equation. And by gathering terms, we can get this matrix we'll call W, and this matrix we'll call V. So we're almost there. We have SY equals WY plus VU. It's almost what we want with Q and P. But we have this S sitting over here, the derivative of Y, not Y itself. So to get rid of that, what we do is we define the diagonal elements of W to be this matrix D. And we're going to subtract D from both sides of the equation. When we do that, we get SI minus D on the left, and we get W minus D on the right. And now SI minus D is always invertible. When we invert that, we in fact get Y equal to some matrix times Y plus some matrix times U, and we name these Q and P. It's one page of algebra. It's not very hard. But the meaning here is really important. You see, these elements these are real rational functions in the Laplace variable, but they're always strictly proper. That's important because it preserves the causality the interpretation that when I draw an arrow, that arrow really means this thing is affecting that thing. So the causality is preserved through the mathematics as we derive this other representation of linear time invariant systems. That gives us three representations now to work with. We had our original system, the physical interconnection, given by the state space realization. This is the complete computational structure. And then the transfer function, the sparsity dependent of the transfer function for that same system is almost fully connected. Because you see there's a ring here. Only one is not part of this ring that's over here. So it's practically fully connected. There really is a path from U2 and U3 to any other state except for 1. But now we have this intermediate notion of structure, which gives us much more structure than is here. But the assumptions we claim to recover this from data are going to be much milder than what we needed to recover this from data. So, what are these new theoretical problems? I've got 1 minute, I better wrap this up. So, we know that given a state realization, it uniquely specifies a transfer function. Well, similarly, we know that given a state space realization, it uniquely specifies a dynamical structure function because we just went through that derivation. We constructed W and V, and then we created Q and P out of the W and V. So that's uniquely specified. And it turns out that from a dynamical structure function, it uniquely specifies a transfer function. And it's a very simple relationship. You can see that the dynamical structure function is a kind of left factorization of G. So there's something about that. Now the new problems going the other direction. We have this minimal realization problem. Well, now we can define what I call structural realization. Structural realization says, given a dynamical structure function Q and P, can you find a state realization, A and B, that generates it? And you might ask a minimal structural realization, just like we asked a minimal realization question. Now when you say minimal, you have to have in mind a certain complexity measure on the target side. So you have to have a complexity measure over here, over state realizations. And the usual thing that you would use is the order of the system, or the number of state variables. So the minimal structural realization problem would say, find me a state space realization that minimizes the complexity, which is the order, such that the Q and P that comes from this A and B, since that's uniquely specified, is equal to some given Q and P. That's the minimal structural realization problem. But you can also ask an approximation problem. The approximation problem requires another measure. You need some sort of proximity measure over here. And then that problem says, look, find me a state space realization A and B such that the QP that it generates is close to a given Q and P in some measure. Okay? Subject to the idea that the complexity of A and B is less than the minimal complexity needed to exactly get that. Because if it's bigger, then I'll just exactly generate this Q and P, and this will be 0. So the approximation question says, what if I want to work with even simpler systems, even simpler realizations than what's needed to generate a particular Q and P? This is much like model reduction, except what should you use as a proximity measure? I've suggested a complexity measure, the order of the system, but we don't know what proximity measures you should use for this new representation of systems. Likewise, you can define another problem that I call network reconstruction. It says, given a transfer function G, maybe that you've learned from data, find a dynamical structure function that's consistent with it, that generates it. You could ask the minimal reconstruction question, which needs a complexity measure over here on Q's and P's. Like the previous minimal problem, that would say, minimize over all choices of Q and P the complexity of your QP representation, whatever that is. Maybe it's the number of edges. I don't know. Subject to the fact that the transfer function that Q and P generates is equal to a given transfer function. Like the previous structural realization problem, you could also ask an approximation question. But the approximation question demands a proximity measure on transfer functions. Now we have those. So we could use one of the many that we might use, like the H-infinity one. And then that problem looks like, find a QMP such that the G that's generated by your QMP is close to a given G in the infinity norm. Okay, subject to the fact that the complexity of your QMP is less than whatever is minimally necessary to exactly generate this G. And again, how do you measure that complexity? I don't know. These are open questions. Okay, these introduce some new theoretical problems, and because I'm out of time, I'm actually wanting to stop my lecture here. I'm sorry I was only able to give you a tutorial on what we're working towards in terms of the theory towards structured systems, but maybe if you're interested, we can talk, but we do have some partial results for a lot of these problems. So we have a number of reconstruction procedures that we use in biochemical reaction orders. We've looked at things like the vulnerability or security of a system in the sense of not losing stability to certain single-link perturbations. And we have new results for decentralized control, so you can design controllers of a given structure that stabilize an unstable plan. And that structure might mean communication structure that you have to respect, because that's simply where the types are. So you just have to respect it. All right. Thanks, guys. I appreciate you having me.
Questions for our speaker? Yeah.
Earlier you talked about measuring every possible condition of those. Aren't you potentially creating an overview problem?
Measuring, what was that saying about measuring all possible correlations of them?
You said that there's a potential combination of measure all possibilities.
Oh, when we were walking through those examples?
Yes. If you're doing that, aren't you potentially creating a overview problem in terms of stability to apply algebra?
Yeah, so it's not going to be overdetermined because the number of parameters that you have, the reason why the structural informativity gets better as you increase the complexity of these models, meaning the reason why state realization is more structurally informative than transfer functions is because they have a lot more parameters to them. So as you move that direction, when you take your input-output experiments and you measure inputs to outputs and you measure these things, you still have so many parameters in your models that you end up being underdetermined. This is part of the reason why you need informativity conditions to restrict that set so that it uniquely specifies one of these more complicated models from the input-output measurements. For the state space realization case, those informativity conditions are too expensive. It's full state measurements. For the dynamical structure case, they're actually much more mild, but they still are there. You still have to make some. You have to bring some other information to the table in order to achieve it. Other questions? Any others? Yeah.
When you're talking about interacting with scientists, usually they have some prior idea of what the system is. Is there either a way to incorporate that into your model, or to just decide whether some connection exists that they must do or want to test it?
Yeah, so the informativity conditions for recovered dynamical structure functions from input-output data precisely mean there's some other stuff about your system that you have to know. And you have to know about it in kind of the right places. Okay? And if you don't, then there's just going to be many answers to the data that you're measuring, and you're not going to know which one is true. So not only do we have a way of incorporating what they already know, but we can tell them which of what they already know is valuable and which is not valuable. You see what I mean? So our whole goal is to try to help them guide the experimental process so they can focus their attention on really bringing to the table some prior understanding of the system that's going to be necessary if they want to answer structural questions about their system before we do the set of identification experiments that can really do the rest of the parameter estimation that needs to be done.
Are you able to handle statistical models?
Yeah, so that's interesting. So there has been some work out of Minnesota and MIT that has formulated a very similar notion of the system as our dynamical structure function, except they take away the inputs, but they assume an independent stochastic process at every node. Now, obviously, that gives you sufficiency of excitation so you can start to do reconstruction and think about answering those questions. But there's a lot, once you all of my talk today, I I haven't introduced the stochastic framework at all. Once you introduce the stochastic framework, there's a lot of new issues that you have to be very careful with dealing with, and probably new opportunities as well. So,
Any other question? 1, 2 questions. You adjudicated. Let's thank our speaker.